Okay, here we go with section 2.3. So in section 2.3, we have something called the Invertible Matrix Theorem. And so what this is doing, there's, parts A through L. There's more parts to this that we add on later, but these are the basics for right now. So an invertible matrix is one that you can find the inverse of. So like we've been learning how to find the inverse of a 2 by 2 and a 3 by 3. They have to be a square matrix to be able to do the inverse. All right, you can't do the inverse of like a 3 by 2 matrix or anything like that. And what's important about this invertible matrix theorem is that once one of these things is true, then they're all true. Or if one is false, then it's all false. And there are a couple of theorems also to note from section 2.2. There's this theorem here in red. If A is invertible, then for each B in Rn, so for each vector in R3, like if you're doing a 3 by 3 or whatever, then the equation AXB has a unique solution, and that would be the inverse times B would be the solution for X. That's what X is. That's how you solve for X. And so there's another theorem in there that I'll talk about later, and that's theorem 6 in section 2.2. Is also this one. If a matrix is invertible, then its inverse is invertible. And basically, if you inverse the inverse, you get back to the original. I mean, that's seems like it should be obvious, but anyway, it's a statement or a theorem. All right, so here we go. So if you start off with a matrix that's invertible, so you have any matrix that you can find the inverse of, it has to be square. It is always going to be row equivalent. If you row reduce it, it's always going to be equivalent to the correct size of its identity matrix. So like if we have a 2 by 2, if you have a matrix that's invertible, you can always reduce it to 1, 0, 0, 1. Okay, so 1's across the diagonal and 0's in the corners. It has n pivots. Well, let's look at this matrix here. Yeah, it has 2 pivots. So 2 by 2 has 2 pivots. The equation AX equals 0 has only the trivial solution. So yeah, like if I put zeros here, if any of these matrices can be brought down to this, if I put zeros on the right, yeah, the answer is the trivial solution. If you set it equal to 0, you're going to have x1 equals 0, x2 equals 0, x3 equals 0, and so on. So that seems to make sense. Letter E, the columns of A form a linearly independent set. Yeah, if you look at the columns, they are linearly independent. Remember, you can reduce them down and take them at any point. They should be linearly independent the whole time. The linear transformation part F, AX, X, if X is transformed by doing A times X, the transformation is 1 to 1. Okay, so yeah, that's what we did that definition earlier in this chapter, 1 to 1. So basically 1 to 1s means you can go back and forth between the sets. Each question has one answer and so forth. All right, the equation AX equals B has at least one solution for each B in Rn. So part G is a little bit weird or a little bit tricky. All right, so this is the one that you're like, at least one solution. So that means it could be infinite solutions. Well, it doesn't, but you can also kind of replace this wording because of this theorem right here. You could almost replace at least one solution with the words a unique solution for each B in Rn, because of this theorem over here that's also true, theorem number 5. So one kind of makes the other one more precise. So think of this, AX equals B has at least one solution for each B in Rn. So I'll come back to that later on when we're doing this example at the bottom of the page. So give me a second to go back to that. The columns of A span Rn. So great. So well, yeah, they span the columns of a matrix up here. These ones span R2. Okay. Letter I, the linear transformation X to AX maps Rn onto Rn. Letter J, there is a n by n matrix C such that C times A equals IN. So basically what's happening there, C is going to have to be the inverse of A for that to happen, right? And then if you multiply it the other way, it has to be true as well. And then AT is invertible. So remember, AT means a transpose, if you transpose the rows and the columns and so forth. All right, so an example one right here, we're going to try to prove that this is, we're going to use the invertible matrix theorem in the easiest way possible to see if this is invertible. So number one, you know, I could always like find the inverse. You know, you can put it in your calculator, and if it has an inverse, it has an inverse. But just to do it by hand, what we're going to do instead is do the some row operations here. So I'm going to see if I can get it to have prove that there's 3 pivots here. We're not going to reduce it all the way down, because once we know there's 3 pivots, then I know that part C is true, and then I can assume the rest. All right, so I'm going to do 4 times row 1 plus row 2 to get rid of that negative 4. I'm going to do negative 2 times row 1 plus row 3 to get rid of that 2. All right, so I have 1, negative 3, 0. 4 plus negative 4 is 0. Up here, negative 3 times 4 would be 12. Negative 12 plus 11 would be negative 1. And 0 plus 1 is 1. In the last row, I'm going to get rid of that 2. Then I'm going to have negative 2 times negative 3, so 6 plus 7 is 13. And then 0 plus 3 on the end is 3. So I'm going to do 13 times, I can already tell that the last 2 rows are not multiples of each other, so it is going to work out. But we'll do 13 times row 2 and add it to row 3. Okay, so 1, negative 3, 0, 0, negative 1, 1. And if you put this matrix A in your calculator and row reduced it, it's going to come out to the identity matrix when we row reduce it, like reduce row echelon form. So that would be a little bit boring every time. So we'll just do these few steps on our own. All right, so I got 0 here. I'm going to end up getting negative 13 plus 13, so 0. Then I'll get 13 plus 3, so 16. Okay, so we have 3 pivots. You know, here they are right here. They're the first thing in each row, and that's it. So what you'd have to say here is you would make a statement after you prove something. You'd be like, oh, look, there's 3 pivots. So therefore, A is invertible by the invertible matrix theorem, because we proved part C, and actually we want to say invertible IMT, we'll put part C. We want to name the part that we said, because once part C is true, then part A is true, and so forth, things like that. All right, so now this question here, example 2, this is going to be what some of your problems are like later on in class. You're going to have to say, you know, given one thing, is the next thing true, and so forth. And so here we go. So we're going to see which part backs up our answer. So if A is invertible, then the columns of A negative 1 are linearly independent. Okay, explain why this is true. Like, what about the statement? So yeah, so basically up here, we're going to use theorem number 6 right here. It says if A is invertible, then the inverse is invertible. Okay, so if A is invertible, well, by theorem 6 from section 2.2, then A negative 1, the inverse, is invertible. Basically, it goes back to A. All right, so once we know it's invertible, then I know I can use anything on my list up above. Like, once I know something's invertible, like I got this, so I have everything, right? And so I can go ahead and say, what do they want me to prove? That linearly independent. So yeah, so I basically have part E. So once A is invertible, then we can say that part E of the invertible matrix theorem says, not S-A-Y-S, says the columns are linearly independent. Okay, so we say yes to that. All right, so letter B. I'm going to change this. I know it says 6 by 6. Let's change this to 3 by 3 because it'll be easier. The example I'm going to use is, I don't want to have 6 things in there. All right, so if we have a 3 by 3 and the equation Cx equals V is consistent for every V in Rn. So this is an important statement for every V in Rn. All right, so when somebody says that this multiplication is consistent for every V in Rn. So what that means, that I have a matrix, right? Let me go back to that question right, oh, crud, sorry. Let me go back to that question right there. So Cx equals V for every, is consistent for every V in Rn. Okay, Cx equals V. So Cx equals V is consistent for every V in Rn. So I have my matrix, my 3 by 3, times some kind of X equals some kind of V, right? So Cx equals V. So this statement is trying to get us to prove so Cx equals V is consistent for every V in Rn. Is it possible that for some V, the equation has more than one solution? Why or why not? So what that means is that I should be able, with this transformation on something here, this is consistent for every V in Rn. So this would be for every V, every vector in R3. And consistent means I can get there. So think of a bunch of vectors in R3, like how about 0, 2, 5? All right. How about 1, 6, negative 8? So that means that with this C matrix right here, with this one right here, you can multiply it by something and get to any one of these things right here. Okay, so to do that, that would mean, like if you want to get to everywhere in 3 dimensions, and if you remember back to what we've done before and watched some of the videos, if you want to get to every place, that means that your columns have to be linearly independent. They can't be multiples of each other. So one vector has, when you have these vectors, these 3 column vectors right here, they have to take you all around 3D space. You can't have one vector and then another vector like lies on top of that, because then it like limits you. You can't get all around. Like your vectors have to go like 3, different ways or whatever. And that way you can get to all of 3D space. That's the best way I know how to explain this. And so that key word, that this is true, the statement appears true for every V in Rn, in R3, in our case, then that means that I always can get there. So that means that my columns are linearly independent. That means that there is like a unique solution. That means I can get everywhere in my dimension space. So based on all that, sorry, that's a long explanation. All right. Is it possible that for some V, the equation has more than one solution? So we're going to say no to this, because my columns have to be linearly independent to be able to get everywhere. They can't be multiples of each other. So what we're also going to go with is part G, right? There has to be a unique place that we get. Also, we could probably say part E, but we're going to go with part G. So part G says, so by part G, matrix C is invertible. All right. And by Theorem 5 in section 2.2, this guy up here, then there is a unique solution. So those two together kind of make this true. Cx equals V has a unique solution. Has to be a unique solution because you have to be able to get everywhere in your dimension space. All right, letter C. If the columns of a 7 by 7 matrix are linearly independent, well, right there, linearly independent, that was important, because once I know this, then I know everything on that list is true. What can you say about the solutions of dx equals b? All right, well, and kind of like the last thing we just did, dx equals b. So this thing by part E, matrix D, is invertible. Okay, so then dx equals b has one unique solution. Okay. All All right, part D. If gx equals y has more than one solution for some y in Rn, that seems like it breaks the rule, right? If you're telling me that this equation has more than one solution, that means there are infinite solutions. So that means my columns are linearly dependent. That means everything fail. So not n pivots. Like you can use like a lot of different rules here. So can the columns of G span Rn? I would say no. And we used parts A, part C we used span Rn, so that is part H. So I would say we mentioned parts what did I say? H and linearly dependent, E, right? So we could mention part H, part E, and so forth. All right, so let's see. Let's go into this last piece right here. So suppose you have a 5 by 5 matrix, and suppose that there is a vector V in R5, which is not a linear combination of the columns of H. All right, so let's make up a little matrix here, 5 by 5, kind of large, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I don't know, I just like to do this just to visually like give myself an idea of what's going on right there. All right, so there's a vector in R5, which is not a linear combinations of the columns of H. All right, so what can you say about the number of solutions of Hx equals 0? All right, so we would know that V is not a linear combination of the columns of H. Now wait a minute. If I have something, if this matrix right here, this is H, I'm supposed to be able to get everywhere. It's supposed to span R5, right? So one of the rules says I am supposed to span all of the R5 space. So if there is something in R5 that I can't get to, then something's wrong, right? All right. So there is a V that is not a linear combination of the columns of H. So basically what we're saying right here is that H times X equals V. It doesn't work, right? There's no solution to this. All right. So that means that Hx equals 0. So basically if there's no solution to that, then H does not span all of R5. So Hx equals 0 does not, so basically everything's false, so that means there's infinite solutions. Hx equals 0 does not have only the trivial solution. All right, so what we did right there is basically I used this rule right here. I used H, right? H was false, so that meant that H was false, which meant that like G was false, which meant then that D was false. Okay, so we kind of went H to G to D, and rules were broken. So H to G to D, it didn't work, right? All right, and this part back here, invertible linear transformation. So these are, we didn't do these a lot, but if you have what's a linear transformation, it's supposed to be true that it doesn't really matter like how you multiply, you still get x back again, because basically either way you multiply an inverse times its original, you're going to, that's like the one time that you can like switch it back and forth. But anyway, you're supposed to get the identity matrix back again. And so it's basically just saying that if you do a transformation to get to here, then you can do like the opposite of the transformation to get to here. Like if you walk 3 steps right, you can walk 3 steps left and get back to where you started, pretty much, right? And this theorem down here too, weren't doing a lot with these things either, so don't worry about that one. But it's just talks about transformations are invertible, and that's it, right? And one more thing I actually want to go over is some of these things here in class. So in class, what we're going to be doing is we're going to be trying to use the invertible matrix theorem to prove like that things are invertible or not. All right. So like if you look at some of these matrices right here, this should stick out to you. This column right here should stick out to you as kind of a failure of, where is it? Linearly independent, like this right there. All right. This number 1 has 3 pivots. You can rearrange the rows and whatnot, but whether the zeros are on top or on bottom, this has 3 pivots. So it should stick out to you in that sense right there. All right. Same thing here. Has 4 pivots, 4 by 4. What could stick out to you in number 3? Maybe you try to actually find the inverse, right? A 2 by 2 matrix. It's easy to, with your little formula, to find the inverse. So maybe actually you find the inverse and it works on number 3. And same thing for number 5. You could find the inverse, or you could look at this and say to yourself, I bet you if you looked at the columns here, if you looked at column number 1 and column number 2, and I think you can find that they're multiples of each other, right? So they're not linearly independent. And you can also do the determinant. The determinant's 0, so you wouldn't be able to find the inverse and so forth, things like that. All right, and then what you're going to do on the next parts down here, you're going to say true or false, and which part which part makes it true or false. Right, and so like number 6, there is a matrix such that AD equals I, and then there's also a matrix C such that CA equals I. Well, those are the unused parts right here, but those are going with parts J, and once part J is true, then part K is true. All right. Number 7, if the columns of A are linearly independent, oh, there it is. So once something's linearly independent, then everything's true on the list. So A spans Rn. So obviously what that would be is that you were given E, which led to H. All right, so you can just say stuff like this, like, hey, this is true. And you just tell me E, I was given E, I went to H, and that's how I knew that was true. Okay, let's look at number 9. If linear transformation Rn maps into Rn, then A has n pivot positions. All right, so into is a bad word right there. It was supposed to say onto. All right, so that's kind of a dumb one, but whatever. We gotta do what we can. All right, so those are true, false. And then down here is kind of what I did in the examples. These are questions that you have to make a statement about, like it's asking you if this, then that, why or why not. And so since I already did, some of those, I won't bore you with some more examples of that, but that's what we're going to be working on. If you wanted to get the front done, you could do that. If you want, the front page, it's not too bad to do. It's a little bit easier because you are given these matrices to work with, and you just want to name the part that you want to do. And, I said here that you cannot use a part of the invertible matrix theorem as proof more than once, but, I don't mind. I mean, I just didn't want you to use the same one over and over and over. Like, oh, I'm just going to row reduce it in my calculator and, oh, they all fail, or, just basically using this fact right here. Okay, so don't just use everything the same. It's the same reason for every problem. So if you wanted to get the front done, you could give yourself a little head start.